Okay, we're going to focus on the light reaction in particular. So let's talk about the big picture. So we have energy from the sun coming in. Here are those stacks of green pancakes, the thylakoid membranes right here. And you're going to have an input of water. It's going to be a source of electrons for us and also hydrogens that we can use to reduce NADP. And as a result of stripping the hydrogens and the electrons from water, a byproduct of that is oxygen. Through the light reactions as well, we will make ATP. Both of these are required to do the Calvin cycle. And at the end of the Calvin cycle, we'll regenerate oxidized NADP, and a byproduct of this will be ADP that will be used all over again. The big ticket item of the Calvin cycle is to reduce the CO2 into sugar, and we'll break that down in just a minute. In your textbook, there's an image that looks like this, another good summary that you can study a bit. Okay, I'm going to jump right into the process of the light reaction, and I want you to know this is taking place right here on these thylakoid membranes. Just like we did the electron transport chain in cellular respiration on the cristae of the mitochondria, now we're going to do the light reaction on the thylakoid membranes of the chloroplast. So in its simplest, here's water. We split water, and as a result you get oxygen and you get some electrons. Now as a result, you also start to build up a hydrogen ion gradient just like we saw before, which we can use to synthesize ATP. So I'll put a pin in that, I'll come back to it. The sun's energy is what gets the electrons excited so that they can do a na-na-na-na-na-na-na, they can do an electron transport chain. And those same electrons will get excited again by the sun and do another na-na-na-na-na. But this time, instead of letting them go all the way down and losing all of their energy, we're going to stop it partway through, and this time we're going to give those electrons to NADP oxidized NADP, in order to make reduced NADP. Now, that's one of the items that we need. A second item that we need is to make some ATP. Both of these electron transport chains that we have here in photosystem 2 and in photosystem 1 will create a hydrogen ion gradient. And so if we start to build up our hydrogen ions inside our hollow green pancakes, our thylakoid membranes, then when those hydrogen ions go back out, when they move back out, you can synthesize ATP, just like we did before. Let me show you a second picture for that. Okay, here we're looking at a pigment complex, several pigments all together on the thylakoid membranes inside the chloroplast. You're splitting water, so you're going to get some hydrogen ions, and you're going to get some oxygen, and you're going to take the electrons away from the hydrogen ions. The sun's energy is going to excite those electrons to a high energy level so that they can go down an electron transport chain, na-na-na-na-na. You're going to use that to bring hydrogen ions inside. Okay, you're going to use those same electrons again, excite them a second time by the sun. This time we're going to let them cool down just a little bit, not lose all their energy, and we're going to give those electrons and some hydrogens to NADP, forming reduced NADP. Now, because we concentrate those hydrogen ions inside the thylakoid membranes, then just like before, we can use ATP synthase complex, and we can allow those hydrogen ions to move back out into the stroma, and we can make some ATP. And we will take this ATP and the reduced NADP to our Calvin cycle in order to build some sugars. I'm going to show you yet another picture of that, because I know it's a lot to take in. I'll blow this up right here. Okay, might be a little blurry, this picture's in your book. If you're reading from the left to the right, there's water molecules here on the left that are getting split into oxygen Here's a hydrogen ion, which we're concentrating inside those green hollow pancakes. And we're going to take the electron from the hydrogen, and the sun's going to shine, and it's going to excite those electrons, and they're going to they're going to go through an electron transport chain, and it's PQ is the molecule that brings the hydrogen ions from the stroma inside those green hollow pancakes, and then we'll take those same electrons and excite them a second time in photosystem 1. And this time, as they get passed through the chain, you can see NADP reductase, and that's what we're going to use, an enzyme to reduce NADP. And as a result of that, we can take NADP, and then as the hydrogens that are concentrated inside the thylakoid membranes go back out through ATP synthase complex, you have ATP. So our end products of the light-dependent reactions are going to be oxygen, which we get from water, from the splitting of water, ATP, and reduced NADP. Of those 3 items, 2 will go on to the next step, the ATP and the reduced NADP, which we will talk about here. You can see. Okay, so we see the light reactions. We know where we got the ATP. We have reduced NADP, and we're going to take those into the Calvin cycle. And I'm going to pause for a bit here. Okay, so let me give you the notes that I didn't give you in the last section. So we're on the electron flow in the light reaction, non-cyclic. This reaction that we just went over is referred to as non-cyclic because the electrons come in and right here from water, and then the electrons go out via NADP. So it's non-cyclic. There's an indoor and there's an outdoor. And so photosystem 2, water is split, forming oxygen and hydrogen. The hydrogen donates its electrons and then becomes concentrated inside the thylakoid membranes. The electrons are excited by solar energy. These electrons move down an electron transport chain, an ETC. Energy is captured by PQ as the electrons move down the electron transport chain and used to concentrate hydrogen ions to the interior of the thylakoid spaces. The electrons are then passed on to photosystem 1. And then number 2, in photosystem 1, electrons are excited a second time by solar energy. The electrons are ultimately passed to NADP, forming reduced NADPH. This NADPH will be used by the Calvin cycle. Now the electron flow in the light reaction for cyclic, and that one I didn't show you last time. Cyclic looks like this. The electrons don't ever leave. They just get excited, and you make some ATP. Get excited, and you make some ATP. There's no reduced NADP formed, and it's not as efficient. You could kind of think of it along the lines as how anaerobic respiration backs up aerobic. This cyclic photophosphorylation would back up non-cyclic. So electron flow in light reaction cyclic, not as efficient as non-cyclic. Water is not split and only ATP is formed. Now back to the ATP production, that section of your notes, right here, okay? The interior of the thylakoid membrane serve as a reservoir for hydrogen ions coming from the splitting of water and PQ, which is bringing those hydrogen ions in. This generates an electrochemical gradient that is used to generate ATP through a process called chemiosmosis. Little letter A, hydrogen ions move from a higher concentration to a lower concentration in the stroma using an ATP synthase complex channel. As hydrogen ions use the ATP synthase complex channel, ATP is formed. ATP is formed. And that's the notes section.